Hi, this is Jeff Gallick with Data Demystified, and this video is a tutorial and a walkthrough of this simulation that I've made to demonstrate how testing accuracy really only works when you have high volumes of testing. So what the simulation is going to show you is what the positivity rate and the new cases per 100,000 is when you actually have different levels of testing, irrespective of what the actual positivity rate is in a population. I really encourage you to watch the full video that I'll link to below that describes the intuition behind all of this, but I'll walk you through the steps in this simulation right now. So there are a couple of parts to this. The first are the ones in yellow. That's where you have your inputs. These are the big assumptions that we're going to be making, and I'll walk through those in a second. The second part is the parts in red. This is the part that tells you what the positivity rate and the new cases per 100,000 will be, depending on how much testing you actually do. So let's start with the inputs. The first one is not the most important, but it needs to be set. This is the population size of the community that you're going to be considering. It's important because we're actually going to look at absolute number of tests, so put a number that reflects your community size. My county, Allegheny County, has 1.2 million people, and so that's what I'm putting over here. So the way the simulation works is that it categorizes people into 5 groups depending on how many symptoms they're exhibiting. So the first group, the most severe, are those who went to a hospital with symptoms. The next group are folks who maybe weren't so bad that they had to go to the hospital, but they did go to their doctor and they had symptoms. The next group stayed home because it wasn't bad enough to actually warrant going to the doctor, but they had symptoms of COVID-19. The next group had close contact with somebody who had COVID-19 but didn't show any symptoms. And the last group are the folks who are just sitting at home, minding their own business. They had no contact with anyone who had COVID-19 and are showing no symptoms at all. These 5 groups are going to differ on 3 key dimensions. The first is how many of them are there, and I'm making some pretty big assumptions here. I'm saying that very, very few people, only 0.02%, which translates into 240 people, actually had symptoms and went to the hospital. That's compared to, let's say, a much larger number, which is most people, about 95%, who don't have symptoms and had no contact. That's going to be about 1.1 million of my 1.2 million people. And somewhere in between I have these other populations. Of course, these are assumptions, and it's hard to know exactly what these ratios are, but you should change them to see what you think makes the most sense for your community. The next metric is the percent likelihood of being infected. What's important is just because you show symptoms of COVID-19 doesn't mean that you actually have COVID-19. Some people are going to have other things like a cold or a flu or another respiratory virus, but we want to know how many of those people actually have COVID-19. Again, I'm making some pretty big assumptions, and you should change these to reflect what you think makes the most sense for your community. I'm saying that folks who went to the hospital that had symptoms, not every one of them has COVID-19. In fact, only 1 in 5 or 20% actually do. And that percentage drops as we get to people who are less symptomatic. The only one of these that I can actually verify with good data is this close contact one. There's pretty good research showing that people who had close contact with somebody who had COVID-19 but are not symptomatic have about a 2.6% chance of actually having COVID-19. The rest of these I kind of extrapolated from there, and again, change these as you see fit. And the last one is a really critical assumption, which is the likelihood of someone being tested, depending on what symptom level they are at. I'm saying that if you went to the hospital and you had symptoms of COVID-19, most likely, 90% of the time, you're going to get a COVID-19 test. Now, that's less true as we go down this list. If you went to the doctor and you had symptoms, you're still pretty likely to get tested, but not everybody will. And as we go down, even fewer and fewer people will get tested. With at the very bottom being folks that are just kind of in the population that don't really have symptoms and didn't have contact are very unlikely to get tested. Only a few of them will actually get that, 1% in my case. Those are all the big assumptions that we have to make. And then the way that this works is it actually says, okay, well, if we ran, let's say, 100 tests down here, well, all 100 tests are going to go to the first group because there's 240 people in that group. Of those, 216 at most will get tested because we only said 90% of them will get tested. And of those 216, 20% will actually be infected. So we find that our positivity rate in this case is 20%, and we see that right here. We also see that the cases per 100,000 is going to be 0.24, and that's just computing the number of people that are infected divided by the total population times 100,000. That's how you get this value. As we test more people, we go into these other groups. So if we run 1,000 tests, the first 216 are going to go to this group, and the remaining of the 1,000 are going to go to this group. And what we see is that changes the positivity rate that we observe to be 12.16%, and the cases per 100,000 to 1.45. What you're seeing is that the cases per 100,000 are going up because we're testing more and seeing more infections, but the positivity rate is going down. And the reason it's going down is because the true population positivity rate is right here, 0.452%. And that's because we have a total of 5,429 people who are actually infected, even though we don't know that from our tests, and that's out of a total of 1.2 million people. Another thing to point out is I calculate the asymptomatic rate here. And so this is just figuring out the people who are not showing symptoms, what proportion of the population of all infected people do they represent. In this case, it's about 75%, which is consistent with things that we know about in the world. So what's worth really pointing out is that as we have more tests, the positivity rate gets closer to the true population positivity rate. And you can see that really nicely if you scroll down to this graph. So this is a graph of the number of tests you conduct, and what it reports out is the observed positivity rate. And you can see the groupings, right? The first few tests that we run, you're going to get that 20% positivity rate because you're only testing the people that are in the hospital that are very likely to be infected. And then as you include more people from the next group, that value goes down to this point here. As you include people from the next group, that value continues to go down to this point here. And then as you include people from the next group, that value continues to go down until you reach this point over here, which is the maximum amount of testing that you could possibly do. And we know that because up here, we see that the max number of people we can test, given the number of people that are tested in each of these categories, is right around 20,554. What's worth pointing out is that we're not going to catch every single positive case because people in these populations are not all going to be tested, just some of them. And so as we test a lot of people, we find that we get to a positivity rate of 2.96 if we test basically everybody, even though the true population new positivity rate is 0.452%. What this is meant to do is demonstrate that as you test more people, the observed positivity rate goes down. That's irrespective of the fact that the true population positivity rate does not change. What I encourage you to do is change these values to reflect what you believe the percent of the population is with each of these symptom levels, how likely they are to be infected, and how likely they are to get tested. And what you'll see is that these positivity rates will change. For example, we might think that there are more people that went to the hospital than 0.02%, so we could change that to, let's say, 0.1%. It takes a second to calculate, and you can see that happening up here. When that bar fills up, we can see that the values down here change, because we now have more people in this first category. In fact, if we run 1,000 tests, we see that it's still at 20%. Now, that's not going to reflect the true infection rate over here, because we're only testing people who are highly likely to be infected. Again, I encourage you to watch the full video that I'll link to below, so that you can understand the intuition behind this a little bit better. I also encourage you to watch a playlist which talks about different ways in which some of these metrics work. And most importantly, stay safe and be healthy.